Welcome to a tutorial on electronics, and in this tutorial we're basically going to discuss today about the voltage divider rule. Okay, so this rule is basically could be derived from Kirchhoff's voltage law. So we'll do the same over here in order to show, or rather in order to display how this rule is basically very useful in terms of circuit analysis and determining how voltages are divided amongst various circuit elements. Okay, so to start with, we first take an example of a simple electrical network. Okay, so alright, so there it is. So in this electrical network, as you can see, we have a voltage source, okay, of EMF value of V, okay, and here we have two other resistors, so basically that's known as R1 and one's R2 over here. So this voltage, okay, basically divides itself amongst the two resistors, that's R1 and R2 over here. Okay, so we just took a very simple two resistor network over here so that you'll be able to grasp the concept much faster. So here we shall basically show how the rule works over here. So let's just first go back to our knowledge, or rather whatever we learned about the KVL. That's the Kirchhoff's voltage law. So Kirchhoff's voltage law stated that well, we could always whenever we'd have some network like this, then the total sum of the voltage drops across the circuit elements as well as the EMF sources, they're taken together, would be equal to 0. So if we do that for this network, then we're basically going to get something like this. We're going to get the EMF over here would be V, okay, that added to the voltage drop across R1, and now this voltage drop over here would occur due to a certain amount of current that would keep on circulating within this network, okay, or rather within this loop. So if I just call that current I, okay, denoted by small I over here, so then the amount of potential drop across R1, okay, would be basically given by IR1, okay, and that across R2 would basically be given by IR2. Alright, so according to the KVL, okay, so I'll just write it down over here from KVL. So we're getting V plus IR1 plus IR2 will get basically equals to 0. So that's exactly what we're supposed to get from KVL. Okay, but what I didn't mention, okay, till now, that this law, whenever we're basically applying it to circuit analysis, has certain conventions, okay, for the signs that we'd basically be using before the EMF sources, before the magnitudes of the EMF sources, as well as the potential drops that are occurring across the circuit elements. Okay, so taking a better look once again. Okay, so just let's get back to where we started from. Okay, no problem. So if we just take a good look at this circuit once again, okay, so we are basically going to be having a current flowing right from the positive end of this positive terminal of this voltage source, okay, and that would just basically circulate about to this network and enter into the negative terminal of this voltage source respectively. Okay, so now let's just call this current I, as we did previously. So now this current, when it's flowing from this positive terminal of this voltage source to its negative terminal, it is basically causing certain potential drops across R1 and R2. Okay, so keeping that in mind, we basically first determine the polarity of the voltages across R1 and R2 in order for using the conventions. Okay, so whenever the current is flowing through R1 in somewhat this direction, then as we know that currents flow from a higher potential to a lower potential, so we can just denote it in this way, that a current flows from a positive potential point to a negative potential point. So whenever the current is flowing from this point, let's say A, okay, to this point, let's say B, then we are having a positive potential right here at A and a comparatively negative potential right here at B. And again, when the current again moves through R2, in the process, okay, it'll create, let's say, let's just call this point C over here. Okay, so just make the points bold, or rather use a different color over here. Let's just use okay, I'll just use red, no problem. So if I just demarcate the points over here, it'll be easier for all to grasp. Okay, so now whenever this current would pass through the resistor R2, okay, so let this point be called C, then this point C would be at a comparatively higher potential compared to this point D, where it'll have a comparatively lower potential, the same as that of this negative terminal of this voltage source, since they're connected together, as you can see. Okay, so now in this process you can see here the potential drop that would occur across R1 due to the current flowing through it would be given by IR1. Okay, that we know, and that across R2 would also be given by IR2. Now since we're having this current, the direction of the current that is flowing through R1 and R2 together, okay, since it's from a higher potential to a lower potential, okay, so we have the current moving from a higher to, from an increased level of EMF to a decreasing level of EMF. Okay, so due to this, we'd obviously include a negative sign between that of IR1 and also before that of IR2. So due to this convention of the current traveling from a positive to a negative point, from a point of positive potential to a point of comparatively negative potential, we'd have a, or rather wherever this sort of polarity would occur, and the current moves from the positive to the negative polarity, will basically be including a negative sign before those potential drops across the circuit elements respectively. Okay, so now by modifying these things in somewhat this way using the convention, okay, now again if we just try to apply KVL over here, then again we'll get something like this. So then from KVL, once again, we're gonna get, or rather if we just utilize the law in a plain simple manner, then we're gonna get the sum of this voltage source plus the drops across that of R1, that's IR1, and across R2, that's IR2. They'll be basically their sum would be equals to 0. Okay, so here we do it over here. Okay, fine. So V plus, okay, minus IR1, okay, and then adding that of R2 over here, that's minus IR2, we'll be basically be getting 0. Okay, so now simplifying this whole thing together, we're gonna get V minus IR1, and that minus IR2 would be equal to 0. And now notice that the current flowing through both R1 and R2 would be the same, because both R1 and R2 are connected in series across the voltage source V. So whenever we have a series connection, okay, over there we'll basically be noticing the voltage divider rule being used to determine the voltage drops occurring across the individual resistors, or rather the individual circuit elements connected across the common voltage source. Okay, so whenever they're in series, that's why the current through both of them would be the same, since the current has got no other path to flow through. Okay, so keeping that in mind, we shall again come back to our equation over here, and now by just applying basic rules of algebra, we can just write this equation in somewhat this way. Okay, IR1 plus IR2. If we take both IR1 and IR2 to the right hand side over here, then we'll be basically getting something like this. And now we can see that I is common in both R1 and R2, and that way if we could just modify it somewhat this way, okay, then we'd possibly be finding out the amount of current that is exactly flowing through each of the flowing through the circuit right over here. Okay, so doing that, we shall basically be getting something like this: V by R1 plus R2. So using KVL, we just found out the total amount of current that is flowing through this circuit over here. Flowing through the entire network, that is. And now we know that the potential drop across that of R1 is basically given by IR1. neglecting this negative sign here, since we're only concerned about the magnitude of the potential drop across R1, if we just use this again, then in that case, so we know that the potential drop across R1 is IR1. So by putting the value of I right over here, we'll basically be getting something like this. The potential across R1 would be given by V by R1 plus R2 multiplied by R1. So here you got your potential drop across R1 only in terms of its magnitude, that is. So it'll have a potential drop of V times R1 divided by R1 plus R2. And now if we go forward and find out the potential drop across R2 as well, this would also be given by IR2, and just by substituting the value of I in the place of that of IR2 over right over here, then we're going to get V by R1 plus R2 multiplied by R2 right over here. So this particular expression gives us the voltage drop across that of R2. I mean only in terms of its magnitude. And now the sign, as we said, that is just a convention to use this sign and somewhat this way in order to make it algebraically, or rather mathematically perfect. So that's why this sort of sign convention is used. But basically we're just concerned about the magnitude. So by using KVL in somewhat this way, we could basically obtain the potential drops across these different circuit elements connected across a voltage source in series. So now this is how the voltage divider rule, or rather this is exactly what we know as the voltage divider rule. We can basically see that the entire voltage from the voltage source, that's V, in both the cases is dividing itself in between that of R1 and R2, okay, in a particular ratio. Okay, as we can see here, if we just compare them together, then we'll basically be getting, okay, if we just take the ratios of both these quantities, then we'll basically get, let's say, okay, let's do it this way. Okay, then we're basically getting over here V R1 by that of R1 plus R2, and then again V R2, okay, by that of R1 plus R2. And if we just take the ratios, we're basically going to get, by simplifying this, these terms will basically cut off with each other. Then we're basically going to get R1 by R2. So over here, this was the potential drop across R1, so we just call it V1 in this case, and that across R2 would be V2. So in that case, we found out that the potential drop across R1 and R2, their ratios are basically in terms of the ratios of their resistances. So from this, we just conclude that whenever we connect circuit elements in series across a common voltage source, then the voltage source divides itself in between, or rather in between that of the circuit elements, or rather resistors over here, in terms of in terms of the ratio of their basic resistances. Okay, so as you can see over here, we obtained this result, which is actually that is given by the voltage divider rule, and that's why it's basically called so. This particular rule is quite important in circuit analysis, and we'll be using this very often. So with that, we come to the end of our tutorial discussion about how to use the voltage divider rule and its basic principles. So I hope you've enjoyed our tutorial, and don't forget to watch our next one. So till then, it's a short goodbye, and thanks for watching.